Hello everyone, Jai Shri Ram. I'm Sanjeev, Sharma, founder of Swayat Robots. At Swayat, we are developing autonomous driving technology that works in highly stochastic traffic dynamics and in unrestricted environmental conditions like in India. Autonomous driving, as you can see, happens to be the most complex and difficult problem to crack for this decade. And doing it in developed countries, like in North American countries or in European nations, is still considered a significant challenge, let alone doing it in India, which is exponentially harder due to varying conditions. This is exactly what we have been doing at Swayat. We are developing sort of a kind of technology that works anywhere for any kind of autonomous mobility application. As a proof of that is our autonomous vehicle over here, which is navigating on very densely cluttered, sort of unmanaged roads in India, where there are no traffic rules to abide by. So autonomous vehicle over here has to use onboard intelligence to compute the motion and behavior commands as to how to navigate from point A to point B and keep itself safe in the environment. This is a very long video. We have done like 84 demos like this over the past few years to validate the technology, the level 4, level 5, supposedly level 4, level 5 technology that we have been developing. As Jan mentioned, we leave it to the audience to decide like at what level we are. So autonomous driving is a combination of 3 key technology pipelines: perception, planning, and localization. Where perception technology processes the visual sensory data and builds a 3D representation of the world around an autonomous vehicle. Location algorithms process this information and determine the vehicle's configuration against pre-computed high-definition, high-fidelity maps of the environment. Planning algorithms then compute the motion and behavior commands to drive the vehicle safely through the environment. There are significant challenges to sustainable autonomous mobility. And the parameters determining that are safety, cost, and scalability. And these parameters, in a nutshell, are affected by the algorithms in those technology blocks, primarily determined by the level of uncertainty that the algorithms can deal with, the capabilities of the algorithm, which will demonstrate what we mean by capability, and also the computational efficiency of the algorithms in those technology blocks. Furthermore, if we can make autonomous vehicles function without requiring high-definition maps of the environment, or for applications like the last mile autonomy applications, if we can make the requirement of maps lot more sparser compared to what the industry norm is, then we can make autonomous sustainable mobility happen. And this is exactly what we have been developing at Swayat. We have been developing algorithms that are much more computationally efficient compared to the state of the art, much more capable, and can deal with the level of chaos that is sort of kind of unheard of typically in the developed part of the world. Furthermore, as I mentioned, like the localization block, so over the past years, we have been developing technology that doesn't make use of high definition maps of the environment for navigating from point A to point B. For very specific applications like the last mile autonomy, even when the use of maps is a requirement, we ensure that our maps are a lot more sparser compared to the industry norm, and are and the inference is also real time against the kind of maps that we have been building. While we are doing all of this, our level 5 R&D also currently focuses on eradication of these compute blocks or the algorithms altogether by building an abstract representation of the environment end to end, where the AI agents can make behavioral decisions for autonomous vehicle to drive it end to end. So now we'll focus on the kind of work that we have been doing at Swayat Robots in each of those technology blocks. So first is perception technology. So as I mentioned, like our focus has been on sustainability and all the parameters that affect the sustainability. So we have been, as you can see over here, we have been developing algorithms that allow autonomous vehicles to perceive its environment, which are as unrestricted as the environments in India, using only off-the-shelf cameras, both during the day and at night. And as you can see over here, even when the delimited information is not clearly visible, our algorithms enable autonomous vehicle to perceive its environment as though inherent environments are unrestricted. So this is what I meant by more capability. One such example is over here. You can see that the vehicle is blinded by the headlight of the incoming truck. And also, the delimited information is not easy to infer over here, where the system actually makes the autonomous vehicle perceive as to how the road is progressing ahead, and also sort of makes the representation of the environment much more structured compared to the inherent environment. So whatever algorithm we have developed, like these are some of the very common algorithms that go into the autonomous driving and ADAS perception block. And every algorithm that we have developed is significantly computationally efficient compared to the state of the art. Usually an order of magnitude computationally efficient in when it comes to perception and planning. So next is mapping. So this is what typical high-definition maps of the environment look like. As you can see, a lot of information is encoded in the maps. Typically, the modern maps also encode the motion primitives that the autonomous vehicles execute on the fly. So we, as I mentioned, like we have been, since our focus has been sustainability, we have been developing maps that doesn't require more than 2 layers, 3 layers of information, whereas the modern maps require like 10 to 15 layers of sort of information that is sort of stored over there. And the GPS maps are more than sufficient for us to enable point A to point B autonomous mobility. When it comes to motion planning and decision making, there are certain class of problems. For example, like we started off with, on the top left, one can see that when we did that demo, embodied intelligence demo, which is a thing now. So we did embodied intelligence before the term embodied intelligence was even coined in the world. So we can see that geofence navigation, any application requiring geofence navigation on campus sort of kind of mobility, doesn't matter the level of chaos that there is, this is a kind of a solved problem for us, with very little to no R&D effort required sort of in enabling those kind of applications. And here's a vehicle sort of navigating through very chaotic environments, typically the kind of scenarios, the kind of chaos that you see on the roads in India. Here we can see these are some of the most complex problems that one can go and solve in the space of autonomous driving. So our vehicle over here, as one can see, is negotiating very tight environments, negotiating the bidirectional traffic coming from the other end, while there's marginally any gap for it sort of to shift here and there. And over the top right, one can see our vehicle is being tasked to cross a toll plaza. So it has to make sequentially optimal decisions to be able to ensure that the vehicle can safely sort of negotiate the traffic at night over there, and also sort of make all the right behavior decisions to successfully cross the toll plaza, just like human beings do. Here one can see also bidirectional negotiation, which is like if any vehicle comes from the other end, the vehicle will have to shift to the off-road patch, which is regular occurrence on roads in India. So if we can solve a class of problems like these, that is the only way to ensure that we can discuss we can negotiate all the corner cases that are typically discussed in the developed part of the world. I'll close this presentation by discussing off-road autonomy. So there are only like 5 entities apart from Swayat that do autonomous, 6 entities that do autonomous mobility off-roads. And in all of those, if you see demos by any of those entities, not even a single startup or even the teams that participate in the US DoD or DARPA have the ability to enable bidirectional negotiation off-roads. This is because the over-dependence of autonomous driving technology on the map. So while one can compute maps for on-road application, it is near impossible to do it off-roads. And that is the reason why, since we have been focusing on onboard intelligence, where we have been making autonomous vehicles to negotiate the level of chaos that is prevalent on the roads in India, we have been able to solve the problem of bidirectional negotiation off-road on a regular basis, just like what we do it on roads. So some of the algorithmic frameworks that we have developed in this space are like significantly competition efficient compared to the state of the art, where our algorithms are usually an order of 2 magnitude computationally efficient. To give you an idea, like if you look at any autonomous taxi company, the replanning frequency of the algorithm is usually around 6 to 10 hertz. Whereas the demos that you're seeing, these algorithms work at like 800 to 3000 hertz on a regular laptop processor. So this is what we have been doing: safer operation, cost efficiency, and scalability. Thank you so much.
Wow, wow.